Hello and welcome to this revision session for AQA A-Level Physics Paper 2 on the topic of electrical fields. So if we've been successful and we've learned in today's revision session, we should be able to answer A-Level Physics exam style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? Well, when you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In this left-hand side section, write down your working out and answers to the questions in the revision session. When you're doing this, make sure you're writing full sentences and show your full working out. Whilst in the right-hand side, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. How should you be revising for A-Level Physics? Well, the first step is to learn the key facts. Use revision guides, class workbooks, student prep books and the textbook to learn the key ideas of the course. You may wish to make mind maps or to write out the notes yourself. Second step is to test yourself. Use things like Caboodle, Seneca, student knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Finally, practice exam style questions. Use exam preparation books, homework books, supervised study books, additional workbooks to answer examination questions and mark your own work. You may wish to download your own examination past papers to do this. So, learn the key facts, test yourself, practice exam style questions. So what are we covering today? We are looking at electrical fields. So what are the key facts to do with electrical fields? Well, we've got Coulomb's law, which is the force between 2 point charges in a vacuum, where F is equal to Q1, Q2 over 4 pi epsilon 0 r squared, where Q1 and Q2 are the charges, r is the distance between the charges, epsilon 0 is the permittivity of free space. Now we can assume air is approximately the same as a vacuum for most practical calculations. Now for a charged sphere, we treat the charge as concentrated at the centre as if it were a point charge. Now we also know that electrostatic forces are vastly stronger than gravitational forces at the subatomic scale. For the electrical field strength, the electrical field lines show the direction of a force on a positive test charge. The electrical field strength is force over charge, or the force per unit charge in newtons per coulomb. The electrical field strength of a uniform field between parallel plates is equal to V over d, where V is the potential difference and d is the separation of the plate. The radial field around a point charge is E is equal to Q over 4 pi epsilon 0 r squared. The work done on a charge is equal to Q times by a potential difference. Now the charged particle trajectories are important, as when they enter a uniform field at right angles, you will get a parabolic path because you got a constant acceleration perpendicular to velocity. Now for electrical potential, absolute electrical potential is the work done per unit charge in bringing a positive test charge from infinity to a point in the field, and it's defined to be 0 at infinity. Our electrical potential difference is the difference in potential between 2 points in a field. The work done on a charge, as we said before, is equal to Q times by the potential difference. There are equipotential surfaces where the potential is constant, and no work is done when moving a charge along an equipotential surface. The radial field potential is equal to Q over 4 pi epsilon 0 r, and our relationship between E and V is E is equal to the change in V over the change in r. So therefore we know that E is going to be equal to the slope of the V against r graph, and the area under the graph is the change in the potential when you've got an E against r graph. So let's now have a look at some general check questions. So, what type of charged object is this? Pause the video now, then unpause the video when you want to go through your answer. We can tell that this is a charged object which is negatively charged, as the field lines are pointing inwards. What type of charged object is this, and how can you tell? This charged object is positively charged, as the field lines are pointing outwards. In electrical field lines, in which directions do electrical field lines point? In electrical field line diagrams, the field lines point in the direction a positive test charge would move in. From a field diagram, how can you determine the electrical field strength of an electrical field? The electrical field strength can be represented by the density of electrical field lines. When do these two objects have the same electrical field? The two objects have the same electrical field in the space up to and to the surface of object 1. When do the two objects have different electrical fields, and why? The two objects have different electrical fields when under the surface of object 1. This is because the charge inside the surface of object 1 will affect its field. What type of electrical field is being produced here? How can you tell? This is a uniform electrical field as the field lines are uniformly spaced apart. What type of electrical field is being produced here? How can you tell? This is a non-uniform electrical field as the field lines are changing in density. Describe what would happen here to a stationary proton. It would accelerate uniformly in the direction of the field lines. Describe what would happen here to the stationary electron. It would accelerate uniformly in the opposite direction to the field lines. Describe what would happen to the stationary proton here. The proton would accelerate in the direction of the field lines, but the acceleration would increase as it moves along as the field line strength increases because the lines are closer together. Describe what would happen here to the stationary electron. The electron would accelerate in opposite directions to the field lines. The acceleration would decrease as it moves along the field, as the field strength decreases as the lines are moving further apart. This diagram shows electrical field lines around three charges, Q1, Q2 and Q3. State the charges of Q1, Q2 and Q3 with a reason. Q1 is a positive charge as the lines are moving away from it. Q2 is a positive as the lines are moving away from it. Q3 is a negative as the lines are moving towards it. In the following diagram, which charge is the more positive charge and which charge is the more negative charge, and why? L is the positively charged object as the field lines are moving away from it. M is a negatively charged object as the field lines are moving towards it. In the following diagram, which charge has the greater magnitude and why? L has the greater magnitude as the field lines are closer together compared to that of M. Describe the force exerted between these two objects. Between the two charged objects, there is a repulsive non-contact electrostatic force. Describe the force exerted between these two objects. Between these two charged objects, there is an attractive non-contact electrostatic force. Which object has the greater electrostatic force acting on it, and why? Both objects have the same magnitude of electrostatic force acting on them as both objects. As in this case, the force is always equal in magnitude on both objects. So, which object has the greater electrostatic force acting on it, and why? Both objects have the same electrostatic force acting on it as the force acting on both bodies is always equal in magnitude. Which object has the greater electrostatic force acting on it, and why? Both objects have the same electrostatic force acting on them as the force acting on both objects is always equal in magnitude. Which object has the greater acceleration, and why? The object with the lower mass will have the greater acceleration as F equals ma. If F is the same for both objects, the lower the mass, the higher the acceleration. If the electrostatic force exerted when the objects are a distance of r apart from the centre of charge to centre of charge is F, what is the electrostatic force exerted on both objects? The force will be linked to F is equal to 1 over 16, as at this point F is proportional to 1 over r squared, so the separation is gone from r to 4r, so the force has therefore been reduced by a factor of 16, r4 squared. In this case, what is the electrostatic force on both objects? It would be F is equal to F over 64. As we know, F is proportional to 1 over r squared. The separation has changed from r to 8r, so the force is now reduced by a factor of 64, 8 squared. In this case, what is the electrostatic force exerted on both objects? Now, so, as a result, as the force would be F over 4, as F is proportional to 1 over r squared. So the separation is doubled from 2r to 4r, so therefore the force is reduced by a factor of 4 because it's 2 squared. If the electrostatic force exerted when the objects are touching, in theory you couldn't use Coulomb's law, but let's just assume we can here, it's F. What is the electrostatic force exerted on both objects? The force would be F over 100, as F is proportional to 1 over r squared. The separation has changed from 2r to 10r, so therefore the force has reduced by a factor of 25, 5 squared. At which point will the charged particle experience the greatest force and why? The electrical field strength is the same at all 3 points, and the charge of the object is unchanged, so therefore the force applied to the particle is the same at all 3 points. At which point will the charged particle experience the greatest acceleration and why? As the particle has an unchanging mass and experiences the same force at all 3 points, then the particle experiences the same acceleration at all 3 points. Which laws of physics can be used to explain the motion of the charged particle in this field, and why? The motion of the charged particle can be described by the Suvat equations, as it experiences a constant acceleration in the uniform electrical field. What type of electrical field is produced by the charged object? It's a radial field. What is the relationship between distance and the electrical field strength? Why is this? The electrical field strength is inversely proportional to distance squared, as the electrical field produced is spherical, which has an area proportional to distance squared. From which point does the charged object produce a radial field and why? The object produces a radial field from the surface of the object, as the charge distribution inside the object can affect the electrical field strength. If the electrical field strength is E at the surface, what is it in T and why? The electrical field strength at T is E over 9, as the distance from the centre of the object has tripled, so the field strength drops by 3 squared, 9. A conducting sphere is placed inside a second uncharged conducting sphere. What can you deduce regarding the conducting sphere and why? The conducting sphere is negatively charged, as all of the field lines flow in the direction that a test positive charge would move in. What is the electrical potential at the centre of the charged object and why? The electrical potential at the centre is 0. This is because at the centre there's an equal amount of negative charge above and below that point. They're producing electrical fields equal in size and opposite in direction, and this gives a potential of 0. What type of electrical potential is around the electron and why? The potential around the electron is negative. This is because the potential is negative around a negative charge. Electrical fields are denoted in terms of positive charges, and a negative potential indicates attraction. What type of electrical potential is around a proton and why? The potential around the proton is positive. This is because the potential is positive around a positive charge. The electrical field is denoted in terms of positive charges, and a positive potential indicates repulsion. Which object has the greatest magnitude of electrical potential energy and why? The electron will have the greatest magnitude of electrical potential energy. The neutron has no charge, so will have no electrical potential energy. Where will both objects have the same electrical potential energy and why? Both objects will have the same electrical potential energy at infinity, as the electrical potential energy for all objects at infinity is 0. Which object has the greatest magnitude of electrical potential energy and why? Assume both objects are the same distance from the centre of the sphere. Both objects will have the same magnitude of electrical potential energy, as both objects have the same magnitude of charge and are the same distance from the charged object producing the field. How do, though, the proton and electron in this example have different electrical potentials? Well, the proton has a positive potential as it's positively charged, and the electron has a negative potential as it's negatively charged. So, which object has the greatest magnitude of electrical potential and why? Proton 1 will, as it's closer to the centre of charge. Why does proton 2 not have half of the potential of proton 1, where r is the radius of the positive charge? Even though v is proportional to 1 over r is measured from the centre of the charged object and not its surface. So what is the difference in potential between proton 1 and proton 2, where r is the radius of the positive charge? Well, proton 1 is 2r from the centre of the sphere. Proton 2 is 4r from the centre of the sphere. So as r has doubled, v will half. What happens to the electrical potential as the proton moves away from the proton producing the electrical field and why? As it moves away, the potential decreases. This is because it's moving away from the source of repulsion. What happens to the electrical potential eventually as the proton keeps moving away from the proton producing the electrical field as y? Well, eventually the potential will drop to zero as at infinity the potential is equal to zero. Will work be done in this situation, and how do you know? Work will be done in this situation as the proton is moving to areas of different potential in the electrical field. What work is done in this situation? Work is done by the field causing the proton to repel to the other positive charge. What happens to the electrical potential as the proton moves towards the proton producing the electrical field in y? As it moves towards the central proton, the potential increases because it's moving towards the source of repulsion. Is work done in this situation, and how do you know? Work is done in this situation as the proton is moving between areas of different potential in the electrical field. What work is done in this situation? Work must be done to the object, energy is inputted into the system to overcome the electrostatic repulsion. So what happens to the potential as the electron moves away in y? As the electron moves away, the potential increases as the two charges are attracting each other. So what work is done in this situation? Work must be done to the object, energy is inputted into the system to overcome the electrostatic attraction. How can the potential increase in this situation? When there is electrostatic attraction, the potential is negative, so therefore it must increase to equal zero at infinity. So let's have a look at some exam style questions for electrical fields. A research laboratory is developing an ion trap to separate ions of different charges. The trap consists of two small spherical electrodes, each carrying a charge of 2 microcoulombs and separated by a vacuum gap of 12 centimeters. A single ion of charge minus 1.6 times 10 to the minus 19 coulombs is introduced midway between the spheres and is free to move. Calculate the magnitude of the electrostatic force acting on the ion due to one of the charged spheres. Calculate the acceleration of the ion when released from rest. The mass of the ion is 3.2 times 10 to the minus 27 kilograms. Then a student suggests that increasing the electrode separation would improve separation between different ions. Evaluate this claim. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know F is equal to Q1, Q2 over 4 pi epsilon 0 r squared. It's Coulomb's law. So pop in all the values, and remember now that there's going to be a separation of 0.06 meters. So therefore, because it's been introduced midway, so therefore it's 8 times 10 to the minus 13 newtons. Sorry about that. We know for the next question, E is equal to Q over 4 pi epsilon 0 r squared. Pop in all the values. Now remember it's r squared, so it's going to be 0.06 squared. So it's 5 times 10 to the 6 volts per meter. The direction will be from the positive sphere, so the ion will accelerate towards one of the spheres. We then use F is equal to EQ, so therefore F is going to be equal to 8 times 10 to the minus 13 newtons. A is equal to F over m, so we pop in all the values and we get 2.5 times 10 to the 14 meters per second squared. Now, increasing the separation will decrease the field strength as E is proportional to 1 over r squared. The lower the field will give the smaller the force and the smaller the acceleration. So this makes the ion separation less effective, not more. So the student's claim is incorrect. A greater separation would in fact reduce performance. A prototype medical device is designed to deliver charged particles into biological cells with very high precision. Two small parallel plates 2.5 centimeters apart in a vacuum are charged to create a uniform electrical field. A singly charged ion with a mass of 4.7 times 10 to the minus 26 kilograms and a charge of 1.6 times 10 to the minus 19 coulombs is released from rest at the positive plate and accelerates towards the negative plate. The potential difference between the plates is 320 volts. Determine the force acting on the ion and the work done in moving it across the field. Determine the final speed of the ion when it reaches the positive plate. Then a researcher proposes doubling the plate separation to allow for longer acceleration distance whilst keeping the potential difference constant. Evaluate whether this would affect the final speed of the ion and justify your conclusion. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know E is equal to V over D as it's a uniform electrical field. So we pop in the values and we get 1.28 times 10 to the 4 volts per meter. F is equal to EQ, so you pop that in to be 2.05 times 10 to the minus 15 newtons. Then work done is charge times by potential difference, so it's 5.12 times 10 to the minus 17 joules. We know that in this case the work done is equal to the kinetic energy gained, so it's a half mv squared is equal to 5.12 times 10 to the minus 17 joules. We can rearrange that to get v, so v is the square root of 2e over m. Pop in all the values, you get 1.47 times 10 to the 4 meters per second. Now, doubling d whilst keeping v constant, we know indicates to us that the electrical field strength, which is V over D, will decrease. So the smaller E will lead to a smaller force on the ion, but the work done, which is equal to QV, will stay constant, as neither of those values are changing. So therefore, the final kinetic energy is actually unchanged. So this means that the final speed of the charged ion is actually unaffected. The next question says, two small conducting spheres A and B are placed in a vacuum. Sphere A carries a charge of 4 microcoulombs and sphere B carries a charge of 8 microcoulombs. Both spheres have identical radii and are isolated from other objects. The graph shows how the magnitude of electrical field strength E varies with the distance from the centre of each sphere. Without performing a calculation, explain why the electrical field strength around sphere B is greater than that around sphere A. At a certain point P, the electrical field strength due to sphere A is 9 times 10 to the 4 volts per meter. Point Q is twice as far away from sphere A as point P. Explain with reasoning the electrical field strength at point Q. Then two identical negative charges are placed in the region between spheres A and B. One is placed at a point closer to A and the other closer to B. Discuss the differences in the forces experienced, the potential energy, and the acceleration of each charge. So, pause the video now, then unpause the video when you want to go through your answer. Right, we know that both fields will follow E is proportional to Q over R squared. Now since QB is greater than QA, the field strength for B is always going to be greater at the same radius. Next, we know the field again follows the inverse square law. E is proportional to 1 over R squared. So doubling the field strength indicates doubling the distance indicates the field strength becomes 1/4. So at that point we can work it through to say that it's going to equal 2.25 times 10 to the 4 volts per meter. Now, next one, we know the electrical field strength is greater closer to the more charged sphere. So the force on each charge is equal to EQ, so it's greater for the charge near B. Now, the potential energy is therefore more negative nearer the higher potential, so closer to B. The greater field near B implies a larger electrical force, so a more rapid acceleration. Now, since both charges are equal and negative, they'll experience a force towards the positive spheres. Acceleration is F over m and is higher near B due to the larger force. So we can say that the charge near A moves more slowly with less kinetic energy gained. The next question says, in the late 1700s, Charles Augustin de Coulomb used a torsion balance to investigate the force between two small charged spheres in air. One sphere was fixed in place, the other was suspended on a light rod and rotated when the spheres repelled. The angular displacement of the rod was used as a measure of force. The experiment was repeated for several different separations between the spheres. Coulomb concluded that the force between the charges is inversely proportional to the square of the distances between them. The following data show the measured force of F and separation R. Use the data in the table to show that the electrostatic force is inversely proportional to the square of the separation between the charges. Support your answer with appropriate reasoning and calculations. Describe how Coulomb may have ensured that only the electrostatic force was measured in this experiment. Identify at least two sources of error that would have been difficult to control in the 18th century. And then modern data loggers and sensors allow this experiment to be repeated more precisely. A student finds that plotting log f against log r gives a straight line with a gradient of approximately -2. Explain what this reveals. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, how can you prove it? Well, you carry out that k, the constant, is equal to fr squared for each value. Now, when you calculate for each line or row on the table, you can say that k is the same value for each data point, so the data supports the relationship f is proportional to 1 over r squared. Now, using an insulating stand in dry conditions will help to avoid charge leakage, ensure that there's no objects nearby to disturb the electrical field. It is quite difficult to measure very small angular deflections accurately, and air currents or humidity could also interfere with measurements. Now we know F is proportional to r to the power minus n. So taking logs gives us this idea that log F is equal to log K minus n log r. So a straight line with a gradient of minus n implies a power law relationship. As the gradient is equal to minus 2, it tells us that F is proportional to 1 over r squared. So this is strong evidence supporting Coulomb's original result and validates the inverse square law. A lightweight drone designed for atmospheric monitoring accidentally accumulates a small positive charge as it flies near a positively charged spherical communication tower. The tower behaves as a point charge and has a net charge of plus 2 times 10 to the minus 5 coulombs. The drone has a charge of plus 8 times 10 to the minus 9 coulombs and a mass of 2.5 kilograms. At one point, the drone is stationary at a distance of 12 meters from the center of the tower. The drone is then remotely moved to a position further away at 24 meters. Show that the electrical potential at a distance of 12 meters from the center of the tower is approximately 1.5 times 10 to the 4 volts. Calculate the work done by the electrical field as the drone is moved from 12 meters to 24 meters. State whether this is work done on or work done by the field and justify your answer. Then a safety engineer claims that the electrical field strength and potential are both halved when the drone doubles its distance from the tower. Assess the accuracy of this statement. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that V is equal to Q over 4 pi epsilon squared R. So you pop in all the values and you get your answer to be 1.5 times 10 to the 4 volts. Now we can work out the potential difference now at 24. So when you work it through, you can get your answer out and you'll find it to be 7.5 times 10 to the 3 volts. So the potential difference is the two values minus each other. So we get minus 7.5 times 10 to the 3 volts. Now therefore the work done is the charge times by this potential difference, which is minus 6 times 10 to the minus 5 joules. Now the negative sign produced in the answer means that the field does negative work. The drone is moving against repulsion. So the work is done by the external agent, not by the field itself. Finally, electrical potential varies as V is proportional to 1 over R. So when R doubles, V halves, which is correct for the potential. But the electrical field varies as E is proportional to 1 over R squared. So when R doubles, E becomes 1/4. So the engineer was partially correct. The potential halves, but the electrical field strength will reduce more sharply. Two small autonomous satellites A and B are used to study long-range electrostatic repulsion in space. Each satellite has a mass of 120 kilograms and is equipped with small ion engines and an external surface that can be charged. In a test, they are both given identical positive charges of plus 5 millicoulombs. They are released from rest in deep space at a distance of 8 meters apart. Determine the initial acceleration of satellite A. Using the principles of energy conservation, calculate the maximum separation the satellites will reach before coming to rest, assuming no other forces act on them. A graph is plotted showing the electrical field strength at various distances from satellite A and how it varies with distance. The graph follows an inverse square relationship. Explain how the gradient of the VR graph for satellite A is related to this electrical field data, and use your understanding to describe how a plot of potential energy versus distance for satellite A and satellite B would appear. Then a student suggests it would be possible to place a small negatively charged probe at a specific point between the two satellites so that it remains stationary. Would this happen, and why? So pause the video now, then unpause the video when you want to go through your answer. In the first one, F is equal to Q squared over 4 pi epsilon 0 R squared. We say Q squared as they both have the same charge. So we work it through to be 3.5 newtons. A is equal to F over M, so it's 2.9 times 10 to the minus 2 meters per second squared. Now the total energy at the start will be all potential energy. So E is equal to Q squared over 4 pi epsilon 0 R. So we work it all through and we get E to equal 28.1 joules. Now at the max separation, the relative speed will be equal to 0. So therefore all energy is stored at the potential. So we know R is going to be equal to Q over 4 pi epsilon 0 E. Pop in all the values, we get 8 times 10 to the minus 3 meters. So this tells us that the satellites reach 8 kilometers apart before turning. Now the next one, we know the field strength is equal to minus V over E. So at that E over R, my apologies. So the gradient of the VR graph gives you negative E. So the V versus R graph will be negative, a negative curve flattening out with increasing R, like 1 over R. The potential energy graph for A and B will rise steeply at small r's and then flatten, which is consistent with repulsive interactions. Finally, the electrical field due to A and B at a midpoint both point away from each satellite. So for a negative probe, forces act towards the satellite from both directions. So there'll be no stable point unless asymmetry is introduced. So the student's claim is incorrect. There's no point of zero net force between two light charges for the negative probe. So only the possible would be if one was positive and one was negative. The diagram here shows a simplified version of the apparatus used in an experiment to determine the charge on an electron. Negatively charged oil drops are sprayed into a region above two parallel metal plates. The plates are separated by a distance d. The oil drops are allowed to enter the region between the two plates. A potential difference V is applied, which causes an electrical field to be set up between the plates. The diagram shows one oil drop falling between the plates. Add lines to the diagram to show the electrical fields between the plates. V is gradually increased. At a particular value of V, the oil drop stops falling and remains stationary between the plates. Explain this observation. Then the oil drop has a mass m and a charge q and stops falling when V equals 5000 V. Show that Q over m for this oil drop is about 50 microcoulombs per kilogram. D is equal to 2.5 centimeters. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you would draw vertical and equally spaced parallel lines when it should be, because it indicates to us we've got a uniform electrical field and the arrows point downwards because it is the direction that the positive test charge would move in. Now this tells us there will be an upward electrical force which is equal to the downwards force of weight, so therefore there's no overall resultant force. We know F is equal to EQ, which we know is VQ over D, and that will equal the weight, which is mg. So Q over m is equal to GD over V. Pop in all the values and we get 4.9 times 10 to the minus 5 coulombs per kilogram. Coulomb's law for a force F between point charges Q1 and Q2, which are a distance r apart, is given by the equation F is equal to Q1 Q2 over 4 pi epsilon 0 r squared. Express epsilon 0 in the terms of base units. Electrical fields are caused by both point charges and by parallel plates with a potential difference across them. Describe the differences between the electrical field caused by a point charge and the electrical field between parallel plates. Your answer should include a diagram of each type of field and a reference to electrical field strength. Two small spheres, L and M, are attached to a non-conducting thread and suspended from a point P. Each sphere is given an equal positive charge of 4 times 10 to the minus 7 coulombs. The spheres hang in equilibrium as shown. The mass of each sphere is 2.7 grams. By considering the forces acting on one of the spheres, calculate the tension in the thread and the angle theta. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that F is equal to kg m seconds to the minus 2 because F equals ma. We know that Q, which is charge, is equal to current times by time, so it's going to be amp seconds. So therefore, we pop that into the equation and we cancel them through. Obviously, R will just be m. You get a squared kg to the minus 1, m to the minus 3, seconds to the minus 4. Now, you should have for the parallel plates a minimum of 3 parallel equispaced lines touching the plates. The diagram for the point charge should be 4 equispaced radial lines touching the charged point. Then the diagram of the fields will be correct and pointing in the direction of positive charge will move in. The parallel plate will have an electrical field strength the same at all points, whilst for a point charge, the field strength obeys the inverse square law. Now for this last question, we know the weight of the sphere is mg, so we work it through to be 0.026 newtons. The electrical force is Q1 Q2 over 4 pi epsilon 0 r squared. So you pop that in, work it through to be 0.023 newtons. Vertically, because it's at an angle, we know we can resolve and we get T cos theta equals mg. And horizontally, we resolve, we get T sin theta equals the electrical force. So therefore tan theta, which is sine over cos, is going to be equal to the electrical force over the weight. So it's 0.023 over 0.026 newtons. So we can work out our angle to be 41 degrees. We then can say, well, if we know T, if we know the angle, well, T is mg over cos theta, because we know all the values there. We can then work it through and we get T therefore to equal 0.034 newtons. So, thank you for watching this revision session today on electrical fields. If we've been successful and we've learned in today's lesson, we can answer A-Level Physics exam style questions on electrical fields, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. Thank you so much for watching this revision session on AQA A-Level Physics Paper 2 on the topic of electrical fields. Thank you so much and have a lovely day. Hello and welcome to this revision session for AQA Physics Paper 2 on the topic of electric fields. So in today's revision session we're going to be looking at how to answer examination questions on A-Level Physics Paper 2, in particular the topic of electrical fields. So if we've been successful and we've learnt in today's lesson, we should be able to answer A-Level Physics examination style questions on electrical fields, assess our understanding on A-Level Physics topic electrical fields, and understand what topics of the electrical field module we need to improve upon for A-Level Physics. So how should you prepare for revising in this revision session? Well, when you're completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. When you're doing this, make sure to write in full sentences and to show your full working out. Whilst on the right hand side, write down any pieces of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. Now, how should you be revising for your A-Level Physics examinations? Well, the first step is to learn the key facts, learn the knowledge. So use revision guides, class workbook, student preparation notes and the textbook to learn the key ideas of the course. You may wish to make mind maps or to write out notes yourself. Second step is to test yourself. So use the Caboodle e-learning platform, the Seneca e-learning platform, student knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Then the third step is to practice. Practice examination questions. So use exam prep books, homework books, supervised study books, additional workbooks to help answer examination questions and to mark your own work. Now you may wish to download your own examination past paper to do this. So the three steps of learning the key facts, then testing yourself, and then practicing exam style questions will help you to revise for your A-Level Physics examinations. Now in this revision session you'll find three types of questions. The first one is a general check question. So these are basic questions designed to probe your understanding of the key concepts of a topic. The second one is a checkpoint. So these are more challenging questions designed to place your knowledge and understanding of the topics into different contexts and applications. Then finally you've got your assessment point questions, which are past paper exam questions which mimic the type of questions found in public examinations. So with that, let's now have a look at some questions on electrical fields. So the first question says, sketch the electrical field lines near a positive charge of plus Q, sketch the electrical field lines near a charge of negative Q, then sketch the electrical field lines near a larger negative point charge. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important that you can be able to sketch electrical field lines correctly. So this first one, because it's a point charge, all the electrical field lines will meet at that point charge. Now you'll also note that it's going to be a radial field because it's a point charge. And then finally as well, the arrows should be pointing outwards because they will follow the field lines follow the direction a positively charged particle would take at that point in the field. So because positive repels positive, the field lines would be outwards because the positive charge would move outwards. Now for this next one, it's going to be the same pattern except the field lines are pointing inwards now because your negative point charge would attract your positive charge, which is the test in this instance, so therefore they'll be pointing inwards. Now if you've got a larger negative point charge, well, it tells you you've got a stronger force of attraction, so it's still an arrow pointing inwards, but to show field strength in this context you would have to have your field lines closer together because the density of the field line indicates the field strength, so you'd have more field lines per unit area. The next question says, draw the electrical fields between the following charged objects. You've got 5 different pictures there. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to remember that the field lines will always go from a positive to a negative, because that's the direction in which the objects will move in, because that's the direction the test charge would move in. So you'll see here that you've got parallel lines in the plate, because between two charged plates you get a parallel field lines, so you get a uniform field between two parallel plates. They'll also curve slightly outwards once you pass the plate boundaries. The next one, again, you've got the field lines going from the positive to the negative, like so. Again, here you've got the radial field going outwards, meeting that plate there to go through like that. Again, the opposite direction in terms of the arrows for the negative charge, because obviously the field lines will move in the direction that the test positive charge will be in. And then finally here you've got your radial field all pointing outwards, because it is a positive charge. The next question says 2-point charges of 2 nanocoulombs are separated by a distance of 1 centimetre. Calculate the electrostatic force experienced by each charge. Then, without detailed calculation, state and explain how your answer to the first question would change when the same charge is separated by 3 centimetres. Now, the electrical field at a distance of 5 centimetres from the centre of a charged dome is 3 times 10 to the 4 newtons per coulomb. Calculate the charge on the dome, and then calculate the force between a helium nucleus and a gold nucleus at a distance of 2 times 10 to the minus 14 meters. A gold nucleus has 79 protons and a helium nucleus has 2 protons. So pause the video now, then unpause the video when you want to go through your answer. Right, so this is using Coulomb's law, which is F is equal to Q1 Q2 over 4 pi epsilon 0 r squared. Again, this equation is given to you in your equation sheet, and epsilon 0 is a constant given to you on your equation sheet as well. You pop in all the numbers. Now remember, nano means 10 to the minus 9, and then remember we'll turn centimeters into meters, so it'll be 0.010, and remember it's r squared. So you pop in the values and it's 3.6 times 10 to the minus 4 newtons. Now you'll see from this equation F is directly proportional to 1 over r squared. So when r increases by a factor of 3, when distance or separation increases by a factor of 3, well, then the force will decrease by a factor of 3 squared, which is 9. So you divide your previous answer by 9, so it's 4 times 10 to the minus 5 newtons. The next one, again, we're using the equation to work it through. Now, in this case, we're actually using the electrical field strength equation, which is electrical field strength is equal to Q over 4 pi epsilon 0 r squared, which is the electrical field strength for a radial field, which it will be. It's a charged dome. So you can work it through, make Q the subject, pop in all the values. Remember, centimeters turns into meters. It's a squared for r as well, so it's 8.3 times 10 to the minus 9 coulombs. Then this last one, we are using Coulomb's law again. F equals Q1 Q2 over 4 pi epsilon 0 r squared. Pop in all the numbers. Remember, the proton has a charge of 1.6 times 10 to the minus 19 coulombs. That's a bit of revision from the particles topic. Pop in all the values. Remember, it's r squared, and we get 91 newtons as our force between them. The next question says, calculate the electrostatic force and then the gravitational force of attraction between 2 protons at a separation of 2 femtometers inside a nucleus. Compare the magnitudes of the 2 forces and whether they're attractive or repulsive. And then in Ernest Rutherford's alpha particle scattering experiment, helium nuclei were fired at a gold nucleus. Calculate the repulsive force between the helium nucleus and a gold nucleus when they've got a separation of 50 femtometers. So pause the video now, then unpause the video when you want to go through your answer. Right, again, in this first one, we're using the Coulomb's law for the electrostatic force, and we're using the gravitational force. We're using the Newton's law of gravitation for the gravitational force. So we use F equals Q1 Q2 over 4 pi epsilon 0 r squared. Pop in all the values. Remember that you are given the charges there of both of them. Okay, and you can work that through. It should be 1.6 times 10 to the minus 19. Okay, so they will work through. Okay, and you can work it out like that, and you get 57 newtons. Now again, remember, because they are both the same charge, there'll be repulsive force. You do the same for the gravitational force, which is F equals G m1 m2 over r squared. Pop in all the values. Again, you're given the masses of the protons and neutrons on the equation sheet. You can get that through to be 4.7 times 10 to the minus 35 newtons, and gravity is always an attractive force. So you can do what you can do is you can find the ratio between the two of them, because one is under the ratio of 10 to the 1, because it's in the tens orders of magnitude. One is 10 to the minus 35, so therefore the electrostatic force is 10 to the 36 times larger than the gravitational force. Again, in this next one, we're using Coulomb's law, popping in all the values, working it through, and we get our answer to be 15 newtons out. The next question says, an electrical engineering technician has been asked to carry out an investigation into two charged particles. The technician has carried out some investigation and has found that the charge on the first particle is measured as 0.3 coulombs, which has a repellent force of 172 newtons on a second particle. The second particle is 1.2 meters away from the first particle. Calculate the charge on the second particle. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one again we're using Coulomb's law, so we're saying F equals Q1 Q2 over 4 pi epsilon 0 r squared. Now we're going to use that equation and rearrange it to work out Q2, the charge on the second particle. So you can say Q2 is equal to F times by 4 pi epsilon 0 r squared over Q1. Pop in all the values, then work it through, and we get 9.17 times 10 to minus 8 coulombs. Now it's important to note that this is a positive charge. How do we know that? Well, because it is producing a repellent force with another positively charged particle, so therefore it itself must be positively charged. The next question says, for the point charges of plus 25 microcoulombs and plus 100 microcoulombs separated by a distance of 60 millimeters, calculate the magnitude of forces exerted on the plus 25 microcoulomb charge by the 100 microcoulomb charge. Then 2 point charges plus 4.0 nanocoulombs and minus 80 nanocoulombs are placed 80 millimeters apart. Calculate the magnitude of the force exerted on the plus 4 nanocoulombs by the minus 8 nanocoulombs charge. State the nature of the force. And then 2 point charges are placed a distance apart. The force in each charge at this distance is 40 newtons. The distance between the charges is doubled. Determine the new force that each charge experiences. So pause the video now, then unpause the video when you want to go through your answer. Right, again, we're using Coulomb's law. F equals Q1 Q2 over 4 pi epsilon 0 r squared. You can pop in all the values and you can work it through in case you know that we're going to be turning our microcoulombs into coulombs. Pop in all the values through and we get our answer out to be 5.5 times 10 to the 4 newtons. Again, we're using Coulomb's law here to work it through, and we work it all out by popping in the numbers. We know nanocoulombs means 10 to the minus 9, and we're doing r squared. Remember, millimeters turns into meters, so that's 10 to the minus 3. So we get our answer out to be minus 4.5 times 10 to the minus 5 newtons. Now it's an important idea to note that when you've got a negative force, in this particular instance it's an attractive force, and if you get a positive force in this instance it's a repulsive force. So because it's a negative value, you know the nature of the force is attractive. Now in this next one we know the relationship that F is directly proportional to 1 over r squared. So therefore if the distance doubles, the force will decrease by a factor of 2 squared, so it's 1 over 4. So therefore if it was 40 newtons, it'll now be 10 newtons because the force has decreased by a factor of 4. The next question says, two parallel plates are 4 centimeters apart and have a potential difference of 2.5 kilovolts between them. Calculate the electrical field strength between the plates. A small piece of dust carried a charge of plus 2.4 nanocoulombs moving to the space between the plates. Calculate the force on the dust particle. Then the mass of the dust particle is 4.2 micrograms. Calculate the acceleration of the particle towards the negative plate. And then a small sphere carries a charge of 2.4 times 10 to the minus 9 coulombs. Calculate the electrical field strength at a distance of 2 centimeters from the center of the sphere and 4 centimeters from the center of the sphere. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we're using the electrical field strength equation. Now, because it's between two parallel plates, it's a uniform field, so we can use the equation E is equal to V over D, where V is the potential difference and D is the separation of the two plates. Remember, we convert kilovolts into volts, and we convert centimeters into meters, so we get our answer out to be 6.25 times 10 to the 4 volts per meter. Now in this next question again, we can use the general equation now for the electrical field strength equation, which is E equals F over Q. So therefore F equals EQ. We've just worked out what E is in the previous question, the electrical field strength. Multiply it now by the charge. Remember, nanocoulombs must turn into coulombs, so you work it through to be 1.5 times 10 to the minus 4 newtons. Now again, you're given the mass here and has to work out the acceleration. Now because you've got a uniform field, it tells you you'll have a constant acceleration, so it can actually help and use the equation A equals F over m, or F equals ma. We've got our value for F from the previous question. We know it's 1.5 times 10 to the minus 4 divided by the mass. Now again, we turn micrograms into grams, but so it's 4.2 times 10 to the minus 6, so it's 3.6 times 10 to the 4 meters per second squared. In this next question, we're now, because it's a sphere, have to use the radial field strength equation. So that is E equals Q over 4 pi epsilon 0 r squared. So you pop in all the values. Remember, it says 2 centimeters, but we don't work in centimeters in physics, we work in meters. So you've got to pop it through to be 0.02. Remember, it's r squared, so it's a squared value, so we get 5.4 times 10 to the 4 volts per meter. Now in this next one, you can work it through by either doing E equals Q over 4 pi epsilon 0 r squared, or you could say the relationship is E is directly proportional to 1 over r squared. So therefore, if r is doubled from 2 to 4, well therefore E is going to quarter, because it's proportional to 1 over r squared, so therefore you quarter the previous value, and it's 1.4 times 10 to the 4 volts per meter. The next question says, the electrical field strength is constant close to a conductor. State the field pattern produced by the electrical field lines. Then below shows the field pattern correctly drawn by a student, but with the charges on the sphere and the plate omitted. State the charges on the sphere and the plate, and then suggest how the field pattern below would change if the sphere shown below had a greater charge. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first question, you've got to understand, what does a uniform field look like? So a uniform field will look like the lines being parallel and equally spaced, because the density of the field line shows the field strength. So if you've got a uniform field strength, you've got a uniform field line density. Now in this next one, you can note that the arrows are pointing away from the sphere. Now the arrows point in the direction that a positive test charge would move in. So if they're pointing away from it, it must be getting repelled, so it must be from another positive charge. Now they're going towards the plate, so it must be attracted to the plate, so that will be a negative charge. Now again, how can we indicate what the field would look like? Well, it would still be radial, because it's still going to actually be a sphere, but there would be more field lines at the sphere in that particular area, because the density of the field line shows the strength of the field. The greater the charge, the stronger the field, the more field lines there are per centimeter squared. So the next question says, in a simple model of a hydrogen atom, an electron orbits a proton. The average distance between an electron and a proton in a hydrogen atom is 5.3 times 10 to the minus 11 meters. Firstly, calculate the electrical force on the electron at this distance. Secondly, state the electrical force on the proton. And thirdly, calculate the acceleration of the electron. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, we need to work out the force, so we're using Coulomb's law. So F equals Q1, Q2 over 4 pi epsilon 0 r squared. We know the charge of the electron and the proton is given to you on the equation sheet, but you should memorize from the particles topic, 1.6 times 10 to the minus 19. You pop in all the values. Remember, we're squaring r, so we get 8.2 times 10 to the minus 8 newtons. Now, this question is very interesting because it probes your understanding of what you're working out. Now, in the Coulomb's law, you're working out the force on both of the charged objects. So both the electron and the proton have this 8.2 times 10 to the minus 8 newtons of force acting upon it. Then finally, we know the acceleration is F equals ma. So A equals F over m. So you do F, which you've just worked out, over the mass of the electron. Once again, it's given to you on the equation sheet, 9.11 times 10 to the minus 31 kilograms. So you get 9.0 times 10 to 22 meters per second squared. The next question says, an alpha particle travelling through a partial vacuum is 1 centimeter from an electron. What force acts between them? Is it attractive or repulsive? Then two spheres with identical charges experience a repulsive force of 2.8 micronewtons when they are 12 centimeters apart. What is the value of this charge? So pause the video now, then unpause the video when you want to go through your answer. Right, so again, we're trying to work out the force. Coulomb's law, F equals Q1 Q2 over 4 pi epsilon 0 r squared. You can then work through the values there. Now you'll actually notice that the values from the electron, so the charge there for one of them should be negative 1.6 times 10 to the minus 19. So you pop it through like that, you will actually get a minus 2.3 times 10 to the minus 24 newtons, so the force will be attractive. Again, here we're trying to work out the charge. Now it's important to know you've got two identical charges. So even though we know F equals Q1 Q2 over 4 pi epsilon 0 r squared, we can say Q1 Q2 are the same value, so therefore it's just Q squared. You can pop in all the numbers. Remember, 2.8 micronewtons becomes 2.8 times 10 to the minus 6. Remember, 12 centimeters becomes 0.12 meters. It's r squared. You pop it in, so you get our Q squared to be plus or minus 4.484 times 10 to the minus 18. Square root that, and we get plus or minus 2.12 times 10 to the minus 19 coulombs. It could be both positive or it could be both negative, okay, to get that repulsive force. The next question says, figure 23.22 shows a conducting sphere of a radius 0.80 centimeters carrying a charge of plus 6 times 10 to the minus 8 coulombs resting on the balance. Firstly, calculate the electrical field strength at the surface of the sphere. Then an identical sphere carrying a charge of minus 4.5 times 10 to the minus 8 coulombs is held so that at its centre it's 5 centimeters vertically above the centre of the first sphere. Calculate the electrical force between the two spheres, then calculate the new reading on the balance. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're working out electrical field strength and it's on the sphere. So we've got to use the radial field strength equation. So E is going to equal to Q over 4 pi epsilon 0 r squared. Pop in all the values. Remember, 0.80 centimeters becomes 0.8 times 10 to the minus 2 meters. Pop in all the values. You remember r squared, so you get 8.4 times 10 to the 6 volts per meter. Now we're trying to, in the second one, work out the electrical force. So we've got to use Coulomb's law. So we're going to say F equals Q1 Q2 over 4 pi epsilon 0. Pop in all the numbers. Again, now remember, 5 centimeters becomes 5 into meters, sorry, so it's 5 times 10 to the minus 2 meters. It's a squared value, so you work it through and you get 9.72 times 10 to the minus 3 newtons. Now it's also important to note what's the new reading on the balance. Well, you have the original reading is 0.0482, but now you've got this electrical force that is acting in the opposite direction to the force of gravity pushing down on the balance, so therefore you've got to subtract it from there, so you get 0.0384 newtons. The next question says, in a simple model of a hydrogen atom, an electron orbits a proton. The average distance between an electron and a proton in a hydrogen atom is 5.3 times 10 to the minus 11 meters. Firstly, calculate the electrical force on the electron at this distance. Secondly, state the electrical force on the proton. Third, calculate the acceleration in meters per second squared of the electron, and then show that the total energy of the electron is 13.6 eV. So pause the video now, then unpause the video and you want to go through your answer. Right, so we're working out the electrical force, so once again we're doing Coulomb's law. So we can say F equals Q1 Q2 over r squared, pop in all the values, remember it's r squared, pop it in there, 8.2 times 10 to the minus 8 newtons. That's the same force on both the electron and the proton as we discussed earlier. And we can say F equals ma, so A equals F over m. Once again, you're given m on the equation sheet, so you can pop that through to be 9.0 times 10 to the 22 meters per second squared. Now, how to work out the total energy of the electron? Well, it's orbiting, and if you remember, we have the idea that in the total energy of an orbit, it's the kinetic energy plus that potential energy. We also know that the work done is going to be the charge times by the potential difference. So therefore, what we can say is that the energy is going to be equal to the kinetic energy, a half mv squared, minus E squared over 4 pi epsilon 0 r, because that's going to be our electrical potential energy, because it's going to be your field strength multiplied by another charge to work it through there. You can then rearrange that and you can work it all the way through, as you can see on the screen, until E equals minus E squared over 8 pi epsilon 0 r. Pop in all the values. Now remember, E in this context is actually the charge of the electron, which is 1.6 times 10 to the minus 19 coulombs. Pop it all through and you get your answer out to be 2.2 times 10 to the minus 18 joules. You've also got to be aware of how to convert convert from joules into EV, and you can do that by dividing by the charge of one electron, which is 1.6 times 10 to the minus 19 coulombs. So you get our answer out to be 13.57 EV. The next question says, determine whether or not the electron initially at rest will reach point R shown in the diagram below. Both positive charges are 0.60 meters from R, and explain your reasoning. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you work this one through? Well, it's all about energies again. So you can work out your new potential energy when you're working through from these values. So you can say it's going to be 2 times by minus 5.76 times 10 to the minus 18 plus 2.88 times 10 to the minus 18. So therefore it's going to equal minus 8.64 times 10 to the minus 18 joules. So therefore when we work it backwards, because we can say that, well, potential is going to be this energy over charge. So we divided them by the charge of the electron, 1.6 times 10 to the minus 19, and we get our answer to be 54 volts. Now the potential energy has to be lower because the negative values are the same, but the positive is a smaller value. So therefore the new potential is higher than the original, but because the positive potentials are the same, but that negative potential is got smaller. It's gone from 36 volts to 54. So it can either travel to a lower potential energy, or gain kinetic energy, or travel to a higher potential because that electron is negative. The next question says, below shows two parallel plates 10 centimeters apart. So calculate the electrical field strength between the plates. The potential difference across the plates is 40 volts, and then you calculate the work done on an electron as it moves from plate A to plate B. And then an electron with a kinetic energy of 20 eV is injected into a field at point X. Describe and explain its motion in the space between A and B. So pause the video now, then unpause the video when you want to go through your answer. Right, so firstly, electrical field strength is between two plates, so therefore it's a uniform field. We can use that uniform equation, E equals V over D, but remember we don't use centimeters, we use meters, so it's 40 over 0.01 meters, 400 volts per meter. Work done is going to be the charge times by the potential difference. You'll see the potential difference from the diagram is 40 volts, because we go from 0 to 40, multiplied by the charge of the electron, and we get 6.4 times 10 to the minus 18 joules. So the next question, well, you'll notice that the electron is going to be attracted by B, if you look on the picture, and it's going to be repelled by A. You can tell that because it's going to want to go to the positive charge, which is on the positively charged part of the plate, which is the 40 volts one, so it'll go towards the right. So what will happen is, as it's injected in, the electron will decelerate. It'll not go all the way to the 0 volts, to the A plate. What it'll do is it'll stop at the halfway point, okay, and then it'll return. The next question says, a maintenance engineer services power coating equipment that works on the principle of electrostatic attraction. The charges on two particles have been recorded. The force between the two particles is 8.2 times 10 to the minus 8 newtons. Calculate distance r between the two charged particles. So pause the video now, then unpause the video when you want to go through your answer. Right, so again, we're trying to work out a value when we've been given a force. So we can use Coulomb's law. So we can say F equals Q1 Q2 over 4 pi epsilon 0 r squared. We can therefore make R the subject, but it's going to be r squared. So you work out what r squared is going to be, popping in all the numbers. Now you're given the charges in the diagram, and you're given the distance and you're given the force in the question. So you get r squared to be 2.24 times 10 to the minus 15. Square root that to get your value of r, which is 4.7 times 10 to the minus 8 meters. The next question says, a student is investigating the electrical potential around a point charge Q. Point P is at a distance of 0.65 plus or minus 0.2 meters from Q as shown in the diagram. The potential at point P is 2.1 plus or minus 0.1 volts. Firstly, calculate the value of the point charge. Then secondly, calculate the absolute uncertainty in the point charge. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know what the potential is. We want to work out the charge. So the equation for potential is V is equal to Q over 4 pi epsilon 0 r. You're given that equation on your equation sheet. Rearrange that, make Q the subject, pop in the values, and we get our answer out to be 1.5 times 10 to the minus 10 coulombs. Now you'll notice for Q, it's going to work through to be V times by 4 pi epsilon 0 r. So that tells us we work out firstly the percentage uncertainty in R, which is 0.02 over 0.65. It's the absolute uncertainty divided by the value times by 100, so we get 3%. We do the same for the percentage uncertainty in the potential, which is 0.1 over 2.1 times by 100 is 4.8%. Because you're multiplying the two values in your equation for Q, you'll add the two percentage uncertainties, so that gets you 7.8%. So therefore you work out 7.8% of the answer, which is 1.5 times 10 to the minus 10. So you get 1.17 times 10 to the minus 11 coulombs. The next question says protons are accelerated by an electrical field between the metal plates A and B in a vacuum. Part of the apparatus used is shown. Firstly, explain why the protons are accelerated by the electrical field. Then, a proton is travelling at a speed of 3.8 times 10 to the 5 meters per second at plate A. Show that the kinetic energy of the proton at plate A is 1.2 times 10 to the minus 16 joules. The potential difference between plates A and B is 2.8 kilovolts. Calculate the work done on the proton as it accelerates from plate A to plate B. Then determine the speed of the proton at plate B. Then the distance between A and B is now doubled. The potential difference between A and B is unchanged. Another proton with the same initial speed at plate A is accelerated between the plates. State what effect, if any, this has on the speed of the proton at plate B. You must justify your answer. So pause the video now, then unpause the video when you want to go through your answers. Right, so why is it accelerated? Well, the protons are positively charged, so therefore, because they're charged, they'll experience a force in an electrical field, that's the definition of a field, that will cause acceleration. The kinetic energy, it's a half mv squared, so it's a half times by the mass of the proton given to you on the equation sheet, multiplied by its speed squared, pop it all through, and you get 1.2 times 10 to the minus 16 joules. Then this next question, the work done, is going to be the charge times by the potential difference. So you've got your charge of your proton, you know that, it's given to you on the equation sheet, 1.6 times 10 to the 19, times by the potential difference, 2.8 times 10 to the 3, because we don't work in kilars, we just work in volts. So therefore you get 4.5 times 10 to the minus 16 joules. So how can you work out the speed? Well, we know that the kinetic energy is going to be the initial kinetic energy, which you worked out in the second part, plus this work done, because work is being done on the object as it's accelerated in the plates, in between the plates, sorry, when it's in the field. So now we've got a new kinetic energy, and then we can say it equals a half mv squared. So we know what that value is, we know the mass, we know that we want to work out the velocity, so we rearrange it, we make v the subject, and we get 8.3 times 10 to the 5 meters per second. Now what effect will this have on the speed of the proton? It'll have no effect, because the work done on the proton is the same, because the distance is not a factor in how much work is done. And if it's another proton that goes in at the same initial speed, it'll have its same starting kinetic energy. So therefore the only work done is q times by v. It has the same charge, it has the same potential difference of the plates between it, so therefore the work done is the same. The next question says, firstly, define what is meant by the electrical field strength at a point. Then in a particle accelerator, a proton initially at rest is accelerated between two metal plates as shown in the diagram below. Firstly, calculate the force on the proton due to the electrical field. Then calculate the work done on the proton by the electrical field when it moves from plate A to plate B. Then state the energy gained by the proton, and then assuming that all this energy is converted to kinetic energy of the proton, calculate the speed of the proton when it reaches plate B. So pause the video now, then unpause the video when you want to go through your answer. Right, definition of electrical field strength, you've just got to learn it. It is the force per unit positive charge. Remember, we always define electrical field strength quantities in terms of test positive charges. Everything is done in terms of positive charges. The force will be equal to, well, it'll be equal to EQ, the electrical field strength, times by the charge. So, but first we've got to work out what the electrical field strength is. Now it's between two metal plates, that tells you it's a uniform field, so we can use that uniform field strength equation of E equals V over D. So we can pop in all the values, we got those from the diagram, so you can work that through, multiply them by the charge to work out the force to be 1 times 10 to the minus 11 newtons. Work done, we've just done this before, work done is going to be F times by it's going to be times by the displacement. That's an equation you've looked at when you've done mechanics. So work done is going to be force times by displacement in the direction of the resultant force it acts in. So you've got that force, you know the distance it's moved there, so the work done is 8 times 10 to the minus 13 joules. That's the work done on the proton, so that's how much energy is gained by the proton, because work done means either energy gained by the object or lost by the object. And then to work out the speed, you can say kinetic energy is a half mv squared. Okay, you know the work done is 8 times 10 to the minus 13, which in this instance is the kinetic energy gain, so you can work out v. You know the mass of the proton before because it's given to you in the equation sheet. You pop it all through and you get 3.1 times 10 to the 7 meters per second. So that brings an end to our revision session today. So hopefully in this revision session you've looked at how to answer A-level physics examination style questions. You can assess your understanding on A-level physics and understand what topics you need to improve upon for A-level physics for the electrical fields module. So thanks so much everyone to listen to this revision session on electrical fields for the AQA A-Level Physics paper 2. Thank you so much and have a lovely evening. Hello and welcome to this revision session on electric fields and capacitance, which is part of the AQA A-Level Physics course for paper 2. So in today's revision session we're going to look at how to answer examination questions on the topic of electrical fields and capacitance for AQA A-Level Physics. So if we've been successful and learned in today's revision session, we should be able to answer A-Level Physics examination style questions, assess your understanding on A-Level Physics, and then finally understand what topics you need to improve upon for A-Level Physics, especially in paper 2. So how do you prepare for this revision session? Well, when completing your work in this revision session, divide your piece of paper into 2 sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your work and answers to the question in the revision session. When you're doing this, make sure you write in the answers in full sentences and show your full working out. Also on the right hand side, write down any piece of information which you find useful, any hints and tips on answering questions from this revision session. And at the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising AQA A-Level Physics? So the first step is to learn the key facts. Use the revision guides, the class workbooks, the prep notes and the textbooks to learn the key ideas of the course, and you may wish to make mind maps or write out notes yourself. The second step is to test yourself. Use Caboodle, Seneca, your knowledge checkers to quickly test your own knowledge, and you may wish to do this retrieval from your own cue cards. Then step 3, practice exam style questions. So either use the exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work, and you may wish to download your own exam past papers to do this. So your 3 steps of learn the key facts, testing yourself and practicing examination style questions will help you in your preparation for revising AQA A-Level Physics. So what part of the specification are we covering in today's revision session? Well, we're going to be looking at 3.7.3 electrical fields, which includes ideas on Coulomb's law, electric field strength, electric potential. We're then also going to look at 3.7.4 capacitance, which covers the definition of capacitance, parallel plate capacitors, energy stored by a capacitor, and finally capacitor charge and discharge. So let's have a look now at a few multiple choice questions on electrical fields and capacitance. So the force between 2 point charges is F when they are separated by a distance r. If the separation is increased to 3r, what is the force between the charges? So pause the video now, then unpause the video when you want to go through your answer. Right, the answer here is going to be D, because we should know that the electrical force equation, Coulomb's law, is given by Q1 Q2 over K R squared, where K is the constant, 1 over 4 pi epsilon 0. So this tells us that if R is increased to 3R, well therefore F is going to become F over 9, because we're dividing by R, but because it's R squared, 3R becomes 9R squared when it works it through, so therefore it's F is F over 9 now, so our answer is D. The next question says, the diagram shows 2 patterns of field lines X and Y around a particle. Which row is correct when the particle is a proton? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer for this one is C, because electrical field lines show the direction a positive charge would take, and gravitational field lines show the direction a point mass would take. So because gravity is always an attractive force, the field lines should be pointing inwards, because the two massive objects will be attracted to each other. But for the electrical field lines, because the direction a positive charge would take, it should be pointed away from the proton, because positively charged particles will repel a proton, so therefore they'll be pointed away from it. So therefore the electrical field is going to be X, whilst the gravitational field is going to be Y. The next question says, 2-point charges of magnitude Q are separated by a distance r. The electrostatic force experienced by each charge is F. What force will be experienced by each of the 2-point charges of magnitude 3Q separated by a distance of 2r? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer here is C, because like I said before, Coulomb's law says that F equals Q1 Q2 over KR squared, where K is 1 over 4 pi epsilon 0. So if R becomes 3R and each Q becomes 3Q, well therefore we can say F is equal to 3Q times by 3Q over K over 2R all squared. So therefore 3 times by 3 is 9, 2 squared equals 4, so it's going to be 9F over 4. So our answer is C. The next question says, the diagram shows two parallel plates. They're conducting plates, and a graph of the variation of the potential between the two plates is shown. What is the magnitude of the electrical field strength between the plates? So pause the video now, then unpause the video when you want to go through your answer. Right, you should be aware that in a VR graph, okay, the gradient of the line is the electrical field strength. So when you're using our VR graph, we can work out our gradient, because it's going to be the change in y, which is 800, 0 to 800, divided by the change in x, 0 to 0.02, because we're working centimeters, remember, we work in meters, sorry, and the graph is given in centimeters. So therefore it's 800 over 0.02, which is 40,000 newtons per coulomb. The next question says, the graph shows the variation in the electrical field strength E with a distance r from the centre of a charged body. What is the potential difference between a point where r equals 20 centimetres and a point where r equals 40 centimetres? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer is going to be B, because you should be aware that in an ER graph, the area under the curve is the potential difference. Now therefore we've got to work out our area from 20 centimeters to 40 centimeters. So what you can do is work out the area underneath by splitting it up into a triangle and a square and a rectangle. So therefore you can work it through by working out the area of the triangle between 20 and 40 and the square or rectangle between 20 and 40. But the trick you've got to remember is that the y-axis is kilovolts per meter, so you've got to convert those values from for example from 50 to 50,000, or from 150 to 150,000. So you work it through and you get 20,000 volts. B. The next question says, point P is a short distance from an isolated positron. What are the signs of the electrical potential and the gravitational potential at P? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer is going to be B, because gravitational potential will have to be negative, because gravitational potential is always negative, because gravity is always attractive. Now in this instance the electrical potential will be a positive, as the electrical field is repulsive, because it's carried out in a field produced by a positive charge, and the positron is a positively charged particle, so therefore you'll get repulsion, which is indicated in potential with a positive value. So our answer is B. The next question says, a capacitor of capacitance 9 nanofarads has plates with overlapping areas of 18 centimeters squared separated by a dielectric of thickness 0.15 millimeters. What is the relative permittivity of the dielectric? So pause the video now, then unpause the video when you want to go through your answer. Right, so what you've got to do is you've firstly got to make relative permittivity the subject of the equation. Now the equation is given to you in your equation book, but it has capacitance as the subject. So you rearrange it and make relative permittivity ER the subject of your equation. So you say ER is equal to C times by D over A times by epsilon 0. Now epsilon 0 is given on the equation book, it's 8.85 times 10 to the minus 12. We know what C is, the capacitance, it's 9 times 10 to the minus 15 because we're working through as in nanofarads, and we know what the diameter is, the distance between the two objects is, it's going to be 0.15 times by 10 to the minus 3 because it says 0.15 millimeters, and we know what the area is, it's 18 times by 10 to the minus 4 because we need to work in meters squared, and to convert from centimeters squared to meters squared is times 10 to the minus 4 because centimeters to meters is times 10 to the minus 2, and there's two of them, so it's 10 to the minus 2 and 10 to the minus 2, which is 10 to the minus 4. You can work that all the way through and you get your answer out to be 85, which is given to be 8.5 times 10 to the 1, which works it through to be A. The next question says, a capacitor of capacitance 10 microfarads is charged through a resistor R to a potential difference of 20 volts using the circuit shown. When the capacitor is fully charged, which of the following statements is incorrect? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer here is going to be B, because if we work out the energy stored in the capacitor, we say E equals a half CV squared. So it's a half times by 10 to the minus 10 times 10 to the minus 6, because we're going from microfarads into farads, times by 20 squared, which is the potential difference. So we get 2 times 10 to the minus 3, which is 2 millijoules. So the energy stored by the capacitor in theory should be 2 millijoules. However, that's not the total energy stored, as some energy is wasted in the charging process, so therefore B is going to be incorrect. The next question says, a voltage sensor and a data logger are used to record the discharge of a 10 millifarad capacitor in series with a 500 ohm resistor from an initial PD of 6 volts. The data logger is capable of recording 1000 readings in 10 seconds. After a time equal to the time constant of the discharge circuit, which of the rows gives the PD and the number of readings made? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer here is going to be D, because firstly, after one time constant, V will be at 37% of its starting value. Now, its starting value is going to be its maximum, which is going to be the EMF of the source, which is 6 volts. So after one time constant, you do 0.37 times by 6, because that's 37% of 6, which is 2.2 volts. Now, the time constant is equal to RC, which again is given to you on your equation book. So it's R, which is 500, times by C, which is 10 times 10 to the minus 3, because we go from millifarads into farads, so therefore it's 5 seconds. So in 5 seconds there will have been 500 readings, because there's 1000 readings in 10 seconds, so in 5 seconds there's going to be 500 readings. So our answer is D. The next question says, the diagram shows two particles at a distance d apart. One particle has a charge plus q and the other has a charge of minus 2q. The two particles exert an electrostatic force of attraction F on each other. Each particle is then given an additional charge of plus q, and then their separation is increased to a distance of 2d. Which of the following gives the force that now acts between the two particles? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer in this particular question is going to be A, because you know that F is equal to Q, say F is equal to KQ1, Q2 over R squared. Now again, K is just a constant, so we can just ignore them. So therefore we can say that F is equal to Q1, Q2 over 2R all squared. Now you might think, does the value of Q not change as each one has been given a value of plus a Q? Well, what's happened is we've gone from 1 being plus 1 to being plus 2 because I've added a charge, but a 1 going from minus 2 to minus 1, so actually it's still 2 times by 1, so the value of charge on the top stays the same, but our value of R has gone up by 2, but that's been squared because it's R squared, so therefore F is now going to be F over 4. Now the thing is though, now one has gone from plus 1 to plus 2, and the other's gone from minus 2 to minus 1. We've still got a positive and a negative charge, so they'll still attract each other, so therefore it's an attractive force of F over 4, which is A. Let's now have a look at a few longer questions on electrical fields and capacitance. The first question says, Figure 5 shows a parallel plate capacitor connected to a 3 kilovolt DC supply. The capacitor is made from two identical metal plates separated by 5 millimeters of air. Each plate measures 30 centimeters in length and 20 centimeters in width. Figure 6 shows a side view of the capacitor. Draw on Figure 6 the electrical field lines between the plates, then calculate the electrical field strength between the two plates. So pause the video now, then unpause the video when you want to go through your answer. Well, the first one, remember what we've got to be aware of is that when we're going through this question, you've got to know that the electrical field lines will always go from your value of the highest value to the lowest, the most negative value. So therefore you're going to have at least 4 straight vertical lines because it's a uniform field. Okay, and the arrows are pointing upwards. So you know this because you've got your negative value at the top and your positive value at the bottom there, so it's going to be going upwards. Now the next one, the electrical field strength, well, we know that electrical field strength by definition is V over D. That's just a fact. So therefore we've got our value of V, 3000. We've got our value of D, which is the separation, which is 5 times by 10 to the minus 3. So we work it through to be 6 times 10 to the 5. The next question says the magnitude of charge stored on each plate is Q. Show that the electrical field strength E can be expressed as E equals Q over epsilon 0 epsilon RA, where epsilon 0 is the relative permittivity, or say epsilon R is relative permittivity of air, and A is the area of overlap of the plates. Then calculate Q when ER is equal to 1, then state the electrical properties of a dielectric material. So pause the video now, then unpause the video when you want to go through your answer. Right, how do you answer this particular question? Well, you've got to link a few equations together. The first equation is it's a parallel plate capacitor. So we can say C is equal to A times by E0 ER over D. That's an equation given to you in your equation book. But we also know that C is equal to Q over V, which is just the equation for capacitance. And then electrical field strength, E is equal to V over D. Once again, all these equations are given to you. So what you can do is therefore substitute Q over V into the top equation and therefore rearrange it and make the subject to be V over D, and then at that point substitute E in to work out your value, and therefore you can say E is equal to Q epsilon over epsilon 0 epsilon RA. The next question is legitimately just rearranging that previous equation to say Q equals E times by E0 ER times by A, then popping all the values in. Now you're given ER in the question, you know E0 is 8.85 times 10 to the minus 12, that's given to you in your equation book, and you know your value of A from your previous question, so therefore you can say the answer is 3.2 times 10 to the minus 7. Now the last two values are just facts. It's the properties of dielectric materials, that they are firstly an insulating material, but also they will contain polar molecules or can be easily polarized. The next question says, figure 2 shows a capacitor and a switch S connected to a parallel combination of two resistors R1 and R2. The initial potential difference across the capacitor is 5 volts and the initial charge in C on the capacitor is Q0. Figure 3 shows the variation of log Q over C with time after S is closed. Determine Q0. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important that you can use log graphs when trying to work out values with capacitors. Now it's important to note that you can work out Q0 from a log QT graph because we know that our y-intercept is equal to log Q0. So if you read off your graph, read off your y-intercept, and you'll see that log Q0 is equal to minus 7.4. So what you can then do is work backwards to work out Q0. So if log Q0 is equal to minus 7.4, well then Q0 is equal to e to the power of minus 7.4. So if Q0 is equal to e to the power of minus 7.4, you work it through to get 6.1 times 10 to the minus 4 coulombs. The next question says, figure 6 shows an isolated spherical oil drop carrying a charge of plus 6.4 times 10 to the minus 19 coulombs. Assume that the oil drop behaves as a charged conducting sphere. Firstly, draw electrical field lines onto figure 6 to show the electrical field around the oil drop. Then define absolute electrical potential at a point in an electrical field. Then an oil drop has a radius of 1.4 times 10 to the minus 6 meters. Calculate the absolute electrical potential at the surface of the oil drop. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one it's very important you can show the electrical field lines around the oil drop. So because it's a spherical object, it'll produce a radial field. So you need 6 radial lines which are straight and evenly spaced out, with the arrows going away from the center. Why is that? Because the arrows show the direction that a positively charged object would take in the field, and positively charged objects repel other positively charged objects, so the arrow should be pointing away from it. The next question asks you pretty much to define absolute electrical potential, and the definition is it's the work done in moving a unit charge from infinity to a place in the field. That's the definition of absolute electrical potential, which you should just learn. And then how to calculate the absolute electrical potential? Well, if you look in your equation book, you'll see that V is equal to Q over 4 pi epsilon 0 R. Now, you've got the value of Q. We know it's 6.4 times 10 to the minus 19 is given in the question. We know 4 pi epsilon 0 because we can work those out from our equation book. And we've got R as it's 5.8 times 10 to the minus 5. Okay, as you can see, it's given it to you in the question. So you can work it through like that, and then you get your answer to be 4.11 times 10 to the minus 3. And then that's your absolute electrical potential. The next question says, figure 7 shows the charged oil drop stationary in air in an electrical field between 2 parallel plates. The potential difference between the plates is going to be equal to V. So firstly, draw and label arrows on figure 7 to represent the force acting on the oil drop. Then the potential difference between the plates is now reversed so that the oil drop is attracted towards the lower plate. Explain why the initial velocity of the oil drop is approximately 20 meters per second squared. Then describe and explain the motion of the oil drop after the potential difference between the plates is reversed. So pause the video now, then unpause the video when you want to go through your answer. Right, it's important to note that the question says to you that the oil drop is stationary. So this tells us that the forces must be in equilibrium with each other. So the idea is that when you look at this particular diagram, you're going to have weight acting downwards. So you're going to have mg acting downwards, but then in the opposite direction, you're going to have the electrical force acting upwards, Fe. Now the next question, it indicates to us why is the initial acceleration of the oil drop approximately 20 meters per second squared. Well, that's because in the previous question we said that the two forces were in equilibrium and that the electrical force counteracted the weight of our actual oil drop. Now the acceleration due to gravity, which is linked into our weight for our oil drop, is going to be about 9.81 because it's on Earth. Now if we have, that tells us that the force produced by this acceleration must be equal to the electrical force produced because it's stationary in the air. Now if you reverse the potential difference, you reverse the direction of the electrical force. So therefore we've pretty much doubled the force acting downwards on our oil drop. So now the acceleration has gone from 9.81 meters per second to be double that, which is approximately 20 meters per second squared. Now it says then describe and explain the motion of the oil drop after the potential difference between the plates is reversed. So now there's going to be a resultant force acting downwards on the oil drop because originally the upwards electrical force is now acting downwards. So this tells us that the oil drop will accelerate downwards, but as it accelerates downwards, because it's moving through air, the air resistance produced as the oil drop goes down will increase because it's moving faster, so air resistance gets bigger until eventually we reach a terminal velocity between the air resistance acting against motion and the resultant force of weight and electrical force acting downwards. The next question says, figure 6 shows two charged water droplets A and B in a thundercloud. The radius of A is 66 micrometers and the radius of B is 35 micrometers. Each droplet has a charge of minus 1.2 times 10 to the minus 12 coulombs. Assume that the charge on A and the charge on B are concentrated at their centers. The distance between the centers of A and B is 1.5 millimeters. Calculate the electrostatic force between A and B, and then the movement of air in the cloud causes A and B to move together until they touch. Calculate the work done against the electrical force in moving A and B from the position shown in figure 6 to the position where they touch. So pause the video now, then unpause the video when you want to go through your answers. Right, so how do you answer this particular question? Well, in the first one, we're trying to work out the electrostatic force. So at this point, we know that the electrostatic force from Coulomb's law is equal to Q1 Q2 over 4 pi epsilon 0 r squared. Now we've got the charge Q1, we've got the charge Q2 from our question because it says to us that the charge of each droplet is minus 1.2 times 10 to the minus 12 coulombs. We've got our value for r squared because we know the distance from centre to centre is going to be 1.5 millimeters, so therefore we can say that the value of r is going to be 1.5 times 10 to the minus 3 to give our value through to be 5.8 times 10 to the minus 9 newtons. Now the next one is calculating the work done against the electrostatic force in moving A and B from the position shown to a position where they touch. So the point is we're trying to work out our change in potential, so we can work out our potential energy difference. So we can say that V is equal, our potential is Q over 4 pi epsilon 0 r. So what you can do is you can work out the potential at 1.5 millimeters for one charge, so you work that through and get your value in, okay, and then at that point you can then also work out the potential at 101 times 10 to the minus 6 meters for one of the charges, so you get it to be 107 volts. So what you can then do is you've got your potential difference, so you find the difference between the two values, so 107 minus 7.2, so therefore you get 100 volts, and then you can work out the potential energy difference due to this by doing the potential difference is therefore equal to the work done over the charge, so therefore work done is the potential difference times by the charge, so it's 100 volts times by the charge of the object, which is 1.2 times 10 to the minus 12, so we get 1.2 times 10 to the minus 10. So just to clarify, why do we get the potential at 1.5 millimeters and why at 101 times 10 to the minus 6 meters? Well, if you look through here you can see that that value is that when the difference is going to be 1.5 millimeters in that particular question, and then we're calculating the work done from that position to where they touch, so we're looking at the difference between the two of them. So when they're touching, the centers are different by about, so you can see 66 micrometers and 35 micrometers from center to center at that point, so therefore you can work out what the distance is at that point, and that's the difference between the two of them. The next question says, figure 7 shows a simplified diagram of a thundercloud. The bottom of the thundercloud is negatively charged and the top is positively charged. Y is a point inside the thundercloud. EY is the electrical field strength at Y, so state the direction of EY, and then a charged water droplet is stationary at Y. The weight of the droplet and the force on it due to EY are equal in magnitude. The mass of the droplet is 1.38 times 10 to the minus 9 kilograms. The charge on the droplet is minus 2.1 times 10 to the minus 12 coulombs. Calculate EY. So pause the video now, then unpause the video when you want to go through your answer. Right, firstly, what's our direction of EY? Well, again, the electrical field will always point in the direction from positive to negative because it shows the direction a positive charge will move in. So therefore, it's going to be vertically downwards from the positive charge down to the negative charge at the bottom of the thundercloud, because once again, the direction of the field lines is the direction a positive charge would take. Now, to work out EY, how can we work this through? Well, it says that our water droplet is stationary, so we can say that the electrical force acting upwards is equal to the weight of the water droplet acting downwards. So we can say that our electrical force is equal to EQ, our weight is equal to mg. We're given m in the question to be 1.38 times 10 to the minus 9, so you can work out our weight to be 1.35 times 10 to the minus 8. We can make that equivalent to EQ, and therefore we can say E is going to be this 1.35 times 10 to the minus 8 over the charge of the droplet in the water cloud, and we get 6.4 times 10 to the 3 volts per meter. The next question says, the base of the thundercloud and the ground beneath it can be modelled as two plates of a parallel plate capacitor with air between them as shown. The base of the cloud is circular with a diameter of 2.75 kilometers. The base of the cloud is 340 meters above the ground. Show that the capacitance of the capacitor is about 1.5 times 10 to the minus 7 farads, and that the capacitor discharges when the lightning strikes the ground. The charge stored in the capacitor before it discharges is 87 coulombs. Calculate the energy available for the lightning strikes. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're going to have to use our equation for parallel plate capacitors, which is C is equal to A times by E0 times by ER over D. Now, you're given the value of D from the question is 340 meters, the distance between the two plates. Now, you've been given our diameter for the cloud to be 2.75 kilometers. So therefore, because it's a circle, you can therefore work out the area by halving your diameter to get your radius, but always work in meters. So convert your kilometers into meters, and therefore you can work out your area to be pi r squared, and you get 5.9 times 10 to the 6 meters squared. You've got your value of E0 and you've got your value of ER from the questions. Okay, so what you can therefore do is pop them in to get 1.55 times 10 to the minus 7 farads. Remember, E0 is going to be 8.85 times 10 to the minus 12, and ER is going to be the relative permittivity of air, which is going to be 1. Now, the next question asks you to work out the energy. Now, you've got charge, and you've got the idea of your you've got your charge there, and you've got your capacitance as well. So you can use your equation E is equal to a half Q squared over C. Now you can pop in your values. You've got your charge from the question. You've just worked out capacitance, so you can work out your energy to be 2.4 times 10 to the 10 joules. Look to see what values you've been given in the question and refer to your equations, which are given to you in your equation book. The next question says, figure 6 shows a circuit used to transfer energy to a lamp in a camera flash. A battery of EMF 12 volts and negative internal resistance charges the capacitor when the switch is in a position S1. The capacitor discharges through the lamp when the switch is in position S2. Assume that the capacitor is discharged completely after each use. The capacitor has a capacitance of 0.85 millifarads, so that the energy stored in the capacitor when it's fully charged is approximately 0.06 joules. The lamp emits a flash of visible light when the voltage across it is greater than the minimum voltage V min. The duration of the flash is 55 milliseconds. Assume that the resistance of the lamp is constant and has a value of 31 ohms. Calculate V min. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you're working out energy, but you've been given capacitance in the question, and you know what V is. It's 12 from the information given in the question. So we say E equals a half CV squared, so you get 6.1 times 10 to the minus 2. Remember to convert millifarads into farads by times and by 10 to the minus 3. Now, in this next question, you're trying to work out V min. Now, it's an idea of a capacitor, which is going to be discharging. So we can say that V is equal to V0 e to the minus T over RC. So what you can do is you've got all your values through, because you know what V0 is. It's going to be 12 there. So you know what R is. You've got C in the question because you're given the value of R and you're given the value of C from your previous one. And then you know we can work it all through and you get 1.5 volts. Now, the next question says the charging circuit includes a resistor and a 12 volt battery. The battery transfers a total energy of 50 milliwatt hours during its lifetime. Explain why only half of this energy can be transferred to the capacitor, and then calculate the maximum number of times the battery can charge the capacitor during the battery's lifetime. So pause the video now, then unpause the video when you want to go through your answer. Right, so the idea is that the energy is dissipated in the resistor in the charging circuit. So what you can therefore say is E is equal to a half CV squared. And so therefore what you can therefore do is then if you can work out the energy that's dissipated as it goes into the circuit and then how much is dissipated in the resistor, and you'll see that half of the energy is dissipated in the resistor as it's charging up. Now, the next one is calculate the number of times the battery can charge the capacitor during the battery's lifetime. So the first thing you've got to do is you've been given an energy, but you've not been given it in joules. So you're going to have to convert 50 milliwatts hours into joules. So you do that correctly, you get about 180 joules. Now, to convert from milliwatt, so if you think about the unit is that energy is power times by time. Well, your power is being given in milliwatts and your time is being given in hours. Now, joules is going to be when your power is given in watts and your time is given in seconds. So to convert from milliwatt hours into joules, you multiply by 10 to the minus 3 to turn milliwatts into watts, and then you will also multiply by 3600 to convert your hours into seconds, so therefore that works out to be 180 joules. Now remember, it's half of that because half of it you've said has been dissipated out of the circuit when it's charging up, so you've only actually got 90 joules. And then we know that each charging process is going to be, discharging process is 0.06 joules from the previous question, so we get about 1500. The next question says, the capacitor is then replaced with one of much greater capacitance. Explain how the replacement capacitor affects the duration and brightness of each flash. Then explain how the replacement capacitor affects the number of flashes the battery can deliver, assuming that the capacitor discharges completely each time the flash is used. So pause the video now, then unpause the video when you want to go through your answer. Right, so the idea is, how will the replacement capacitor affect the duration and brightness of each flash? Well, the idea is you've got a much greater capacitance, so therefore you've got a greater duration, or the brightness will decrease more gradually because you've got a greater time constant, so therefore it'll take a longer time to charge and also a longer time to discharge as well. So whilst the initial brightness is going to be the same, it's going to be brighter for longer, because whilst your initial value of charge you're going to have in your capacitor is the same, okay, the time it takes to discharge is going to be longer, so therefore it'll be brighter for longer. The next question says, explain how it will affect the number of flashes the battery can deliver. Well, there's going to be fewer flashes to be delivered because the energy stored in the capacitor is greater, because you know E is equal to a half CV squared, so we know that C has increased, therefore E has increased, so therefore it'll take, the fewer flashes will be delivered each time, so therefore the energy stored is greater, so therefore there'll be fewer of them delivered each one. The next question says, define the electrical field strength at a point in an electrical field. And then figure 2 shows a point charge of plus 46 microcoulombs placed 120 millimeters from a point charge Q. Position P is on the line joining the charge at a distance 66 millimeters from charge Q. The resulting electrical field strength at position P is 0. Calculate charge Q. So pause the video now, then unpause the video when you want to go through your answer. Right, the first one is just the definition of electrical field strength. So the definition is, it is the force per unit charge on a positive charge in the field. So the electrical field strength is the force per unit charge on a positive unit charge. Now, how do you work out the charge, calculate the charge here? Well, you'll notice that there are two charges. There's Q, and then there's the second one, which is going to be 46 microcoulombs, and you'll notice that at the resultant at P is going to be 0, so we can equate the electrical field strength from the left hand side and equal to the right hand side and work out your value. So what you can say is, you can say 46 times 10 to the minus 6 over 4 pi epsilon 0 0.054 squared, which is the distance from that charge on the right hand side to P, is equal to Q over 4 pi epsilon 0 0.066 squared, because again that's the distance from the charge on the left hand side to P. You can then rearrange it all, make Q the subject, and you get Q to be 6.9 times 10 to the minus 5, or 68.7 microcoulombs. And that also makes sense because you'll notice that the two are going to cancel out, and you notice that the 46 microcoulomb charge is actually going to be slightly closer, so therefore that tells us that the charge on Q is going to be slightly bigger to negate the fact it's slightly further away, to give equal electrical field strengths, so they cancel each other out at P. The next question says, a small rubber ball coated with a conductant paint carries a positive charge. The ball is suspended in equilibrium from a vertical wall by an uncharged non-conducting thread of negligible mass. The wall is positively charged and produces a horizontal uniform electrical field perpendicular to the wall along the whole of its length. Figure 3 shows that the thread makes an angle of 30 degrees to the wall. The thread breaks. Explain the motion of the ball. So pause the video now, then unpause the video when you want to go through your answer. Right, so what's going to happen is that you'll notice that when the thread breaks, there's going to be two forces acting on the ball, because you've got a charged ball, okay, and it indicates it's got a positive charge, so it's going to follow the electrical field lines in the horizontal, so the ball is going to accelerate horizontally to the right hand side, but because it's now falling, it will accelerate down vertically downwards due to the force of weight. So therefore we've got our electrical force accelerating to the right and our our weight force accelerating it vertically downwards. So therefore you're going to have acceleration in a straight line at 30 degrees to the vertical away from the wall, because you're going to have two accelerations act on the object, one in the horizontal due to the electrical field and one in the vertical due to the gravitational field. Right, so I hope you've enjoyed this particular revision session where we've looked at answering A-level physics examination style questions on electrical fields and capacitors. So hopefully you feel you can answer those A-level physics examination style questions, you can assess your understanding on A-level physics, and finally understand what topics you need to improve upon for this particular topic. So thank you very much for watching this revision session on electrical fields and capacitance for AQA A-level physics on a paper 2 topic. Thank you very much for watching and have a lovely day.